This session on self-driving vehicles. My name is Jonas Mårtensson. I will be the chair of this session together with
Kristina Ravelli.
Thank you. And we will try to be very strict with the time so we can finish when we are supposed to. So I would like to start by introducing Kristoffer Öfjell from Linköping University, who will talk about visual autonomous road following.
Thank you. So this might not be autonomous driving, more like a fancy cruise control. We've heard much about deep learning and deep stuff and lots of training, so this will be in the completely opposite direction, simply shallow and few sensors. So this is me playing around as an undergraduate, making a teleoperated vehicle several years ago. And the take-home message is, visual is sufficient. You don't need any other sensor. I might step on some people's toes during the presentation. I apologize for that in advance. These things you've seen, you can drive onto the highway and then you switch on the cruise control and automatic steering and just sit back and relax. But as we heard yesterday, there might be snow and mud and stuff. But still you have this driver. He can give you training data on this road. So if you have some not so heavy online learning thingy, you can actually learn a mapping from this visual information to steering. So you just let the driver drive for a while and it's fun to drive. You can drive for a minute. And then the idea is that we've learned what this is, and then when the driver gets tired of driving, you can just let go and let the car drive itself. These are some pictures of roads that have been taken during the years, and as you see, they can be quite different. So those who are into learning all kinds of roads, you're in for a challenge. Yep, we've seen the autonomous cars of the past. They're kind of reducing in sensor, and you have really complex and involved systems. So kind of trying to do something like this instead. A camera, some learning, and steering control. And since we don't want to have any kind of legal issues, we have a slightly smaller system to try this thing on. Great, so just go to the shelf and pick some fancy learning system that has all these fancy words in it. But the problem is you don't find that many systems, especially this online thingy. The convolutional networks are really popular, but you really need it. You don't want to wait a week before the car can drive itself. And you want this multimodality. You want the output to be able to represent several possibilities. Even if you have training data avoiding the moves to the left or to the right, and then the learning system goes, oh yeah, I can reduce noise, take the mean and go straight into the moves. So it's based on this channel representation. So you have, instead of one value, you have a vector that represents different ranges. And you have these soft things, so you can represent stuff with more precision than the spacing of the bins. And when you have a more fancy representation, you can go with really simple learning systems. So just taking out the products and inputs and outputs and adding them, and you get something that is a representation of the joint distribution of the input and output. And for using this mapping, it's a vector matrix multiplication. So it's extremely fast. And you get this multimodal. So in this example, when you have input of 1.42-ish, you can see that it represents two outputs. So either 0.55 or 1.81. And that's useful for moves and intersections and all this stuff. We have added some more stuff into this, like a nonlinear update. If you have this linear thing with the learning rate, that's also the forgetting rate. So when you learn faster, you also forget faster. But you can add this nonlinear stuff to change these two parameters individually. And it's related to this simulated annealing and softmax and stuff. So the idea, you drive the car for a while, it learns, and then we added some kind of immediate reinforcement learning. So when it starts going okay, you can just give it feedback. And the rest of the system is really simple, frame by frame prediction and to steering control. So this is what you can achieve with this really simple approach. We have demonstration auto showing if I'm driving or if the car is driving itself. You have positive, negative indicating if I'm giving it feedback. And we have some representation of the distribution of control signals. So starting with the more fun thing, taking the system out of the lab onto a gravel road. So it started completely untrained. Drive for a while, kind of let it go, see if it goes off-road and correct it. So it's fine time to speed, but yeah, a minute or so of training. And then it goes along happily. And then you might head into one other type of road, like a paved road, and provide some additional training, and then it goes along. And then we tried some lab experiments just to get some number on performance and things like that. So you see some demonstration here and there, but mostly by itself. So this is one single monochrome camera. It's a laptop that is 6 years old by now. It's running only on the CPU. So you don't really need more than that. And then you can, when it kind of goes okay, you can give it feedback instead of demonstrating. And it's simple, just relax and push positive, negative buttons. And we also added so that it will speed up when it gets positive feedback. So as you can see, after it has got this session of feedback, it drives quicker. It goes around one lap at a time. At the same time as it drew 1/2 lap before. Then you have this distribution representation or distribution inspired representation. So you can do stuff like priors. So you have this intersection and you have two options. Then sometimes you might want to choose where you want to go. You don't want to go kind of any road. You want this particular road. So then you can just provide a system with a soft prior, kind of keeping to the right, keeping to the left. But still, this prior can be made weak enough not to push the car off-road. So there will be some example where I will give a right prior, or left prior, when there is only the option of turning right, and the car will continue to the right. So turning left means go off-road, but the car is like, ah, are you sure? Yes, and this continues for some time, so we might look at the next video. Since it's online learning and you don't really have any representation of the road, and it's not biased towards driving on roads, so you might as well teach you something else, like following a person. Note to self is kind of check how wide the camera is. If you go outside the view, then the camera or the system has kind of problems. And some demonstration how confident I am in the system. So this is 5 meters of confidence, leaving the control on the car. Thank you.
Thank you. We even have time for a quick question. We have one. Go sure.
Hello, Robert Budde from Leopold Costal. So, online learning sounds quite interesting and quite tempting, yet when we think of production cars, do you think it will be feasible for every car being uniquely trained by its operator? So in the very end, somebody has to be responsible of the autonomous car, and this, in this case, cannot be the manufacturer, I think.
No, in this case, it must be the driver.
Okay.
And I would say this is not an autonomous system per se, it's a kind of extended cruise control, you might say. I don't think there will be kind of an option of getting rid of all these complicated systems, but this might be an option for, if you have a snow road or mud road or anything where you can't go fully autonomous, you can at least get some kind of semi-autonomous.
Okay, thanks.
Okay, thank you. Then we are going to finish with you. Thank you very much for your presentation, and we are going to the next. Sorry, to the next presentation. So our next presenter, his name is Florian Kuhn from the Forschungszentrum Informatik in Germany, and he's going to present the testing and validation of high-level components for automatic driving simulation framework for traffic scenarios.
Okay, thanks for the nice introduction. Still connected. So I'm Florian Kuhn from the FZI, and I'm here for my colleague Marc-René Zofka, who can't be here today, but he says hello to the audience and he would like to have had this presentation because it's a great honor to present something in this area because there are a lot of works right now, and yeah, it's nice to be here. You can ask him questions directly via email. He would like to have emails, and yes, I will try. Sorry. You can also send him some recommendations and also some some things about our work. This work is about a simulation framework for traffic scenarios and especially for high-level components for automated driving. I would like to start with an example from one of our last projects. This is a valet parking project where you leave the car in front of the garage and the car has to fulfill a lot of tasks inside the garage. It has to communicate with the environment and has to plan, has to maneuver planning, trajectory planning, avoid obstacles and so on. So these are all high-level tasks that we proved to be possible today. It looks a bit like a commercial video, but it was really a live demonstration with a lot of politicians and so on. And during the shooting of this video, we had no failure. We still had a supervisor that could stop the car at any time, but people started to ask, when can we see this in reality? And everybody of you knows that we have to prove that it is robust. And that's where we come to testing and validating such systems. Testing and validating autonomous driving is a bit more than driver assistance systems, where you have, for example, automated emergency braking. You just have a low-detailed, high-level component, and these high-level components are now much more important when we talk about autonomous driving. They include trajectory planning, maneuver decision, vehicle prediction, and also scene understanding, where all of these components base on an abstract layer. We are quite sensor independent and work with objects and try to estimate relations between these objects, estimate future behaviors. For example, here interaction could give us information where our vehicle will go next or where other vehicles go next. So to prove the system on a lot of situations, we need a lot of behaviors of other traffic participants. And that's our approach. We want to test and validate realistic scenarios by realistic traffic participants' behaviors. So how can we cover the space of all traffic participant behaviors? That's not an easy task, and the fixed use case catalogs are no solution for this task. We have a lot of possible situations. This is the set omega here, and we have small simulations that can fulfill a subset of these situations. And the idea is now to combine different simulations, for example, a physics simulation with a traffic flow simulation, to get a larger coverage of this set. What we also want to show is we want to integrate into the same concept the seamless transition between virtuality and reality. That's also an important topic right now, because we want to start in simulation and slowly transition or transfer it to the real vehicle by replacing components, virtual components by real components, and finally test it on the real vehicle. The other thing is that all these algorithms have quite similar input and output, so we want to have one system to test all these algorithms. There are already a lot of works, and 3 of them are quite important for our work. The first one is a taxonomy on testing methods for automated driving. These include virtual and real tests, and we based our concept on this. And the other 2 are the idea of co-simulation between a robot and a traffic flow simulation. And the third one is the real car in a traffic simulation, what's this mix between virtuality and reality. So our concept consists of this. We have this high-level autonomous driving component down here, and we somehow have to stimulate the component by the environment, and also the component interacts with the environment again. The environment is represented by the simulation. There we have 4 models. A scene graph model that represents the entities in the environment, and the logical model that is responsible for the behaviors. This part here is quite ground truth data, and we have to somehow sense this data, add noise and so on to get it realistically, and also we have to intervene in this environment by a physical model. We will start with a scene graph model. This is mainly the instantiation of all the objects in an object-oriented way, and it interacts with the logical model. We have these 2 arrows there. It pushes data to the logical model and also receives data from the logical model. As I said before, it provides the reference data that is very important for evaluating, because we need reference data to compare against. An example is here, we model a window with geometry and reflectance, and later the sensor model can use these properties to model the sensor. The logical model is responsible for the agent's behaviors. There we have to model different maneuvers, for example, lane change and lane following, and also we can model different driver styles. These are dimensions that we can vary later and create a lot of situations this way. What I have to mention here is that it mostly assumes perfect perception to keep runtime low, but you could imagine you can also add here more advanced perception modules. Now the physical model is responsible for the input data from the AD component. So for example, steering the vehicle. This can vary from trajectory interfaces, where you get a whole trajectory, and also more close to the actors, like getting velocity and steering angle. You can model a whole Ackermann steering in there, and yeah, that's the main purpose of this model. The other side is the sensor model, where we imitate realistic perception of ground truth world. That means we would like to have sensor noise in there, but we don't want to create a whole replacement for example, a camera sensor. We have already the obstacle list in the scene graph model, so we could just select objects that are visible from the ego vehicle, and this way we can simulate occlusion and sensor range. But we could also create special measurement spaces, or transform these objects into special measurement spaces. For example, if you have a video sensor, you could imitate a video sensor by saying, I have a camera with a pixel resolution, and I don't give the normal colored information, but already object information that we can sample from the object list. So that's quite a nice feature for evaluation later. So high-level AD component, that's the last point I want to talk about. Here we would like to implement different kinds of testing. We could completely work in simulation, we could add real components, and we would also like to easily transfer it to a real test vehicle. Especially the vehicle in the loop model is quite popular these days, where you have an experimental vehicle on a test ground, and you synchronously run a simulation that gives additional input to the vehicle. For evaluation, or for a small case study, we showed how you could implement this system or this concept with open source tools. For example, you can use Gazebo for the scene graph model, and also for the physical and sensor model basis. And you can add a traffic flow simulation like Sumo for the logical model. For the physical model, we implemented 2 models. One that is a full-featured vehicle, where you can add trajectories or just give values like acceleration and steering angle. And also we added an avatar model, we call it like that because it's just a case of a vehicle and it's placed at a position where another sensor gives us the position. So we can add here the real vehicle, the real localization of the vehicle, and it just gives us the information where the vehicle is. This way the vehicle can be placed and the sensors in the vehicle can recognize the environment in the simulation. Our test was with a vehicle in the loop system, including real components. So everything is in there. And I have a short video where we showed the components. This is the gazebo on the left side. On the right side we have the same situation in Sumo. And now we can drive the vehicles in Sumo. They are automatic driving and they are transmitted to the scene graph model. So we have everything in one scene. This is the real vehicle position that is driving on a test ground. The test ground looks similar to this, and the vehicle can now observe these obstacles via a virtual sensor and combine it with the real sensors in the vehicle. So for example, if we have here a camera sensor, we have this virtual vehicle in there and create dangerous situations without really driving dangerously. I come to the conclusion. We show the concept for testing and validating high-level components. The concept includes 4 models: the scene graph model, the logic model at the center, and then the physics and sensor models around it, what gives us a possibility to create a large spectrum of behaviors. You can see us also in the poster session afterwards. You can recognize the poster by this concept, and I'm happy to answer your questions.
So we have time for one question. Yes, please.
First, thank you for the nice presentation. In your presentation, I see many features about driving simulation. You present mainly the architecture, the different layers, but I do not see how do you generate the dynamic scenario, traffic scenario from this architecture.
The idea is, maybe we go back. The scene graph model is mainly where you can construct the environment by hand. That's a step that you have to do by hand, or you take an algorithm before that to generate the environment. But we think the difficult part is to generate the things in the logical model, because it's hard to define, for example, behaviors and maneuvers by just saying this vehicle has to drive here, has to slow down now, has to drive in a specific way. And we think if you have a traffic flow simulation, you can reduce this to a few parameters for the vehicles, for example, driving style and maneuvers.
My question is, you have some special algorithms to simulate or to produce the different maneuvers or driving style. Is that?
I would say not yet, but it's the basis for creating an algorithm.
It's the concept.
That. Yeah, it's more like you can randomly adjust the parameters to try to cover the space as close as possible. That's the idea.
Okay, thank you.
Yeah.
Okay, thank you very much. Okay, it's time for the next talk by Georg Schildbach from University of California at Berkeley, who will talk on dynamic programming approach for non-holonomic vehicle maneuvering in tight environments, which will soon be ready here.
Can everybody hear me? Yeah, sounds good. Okay, welcome to my presentation on dynamic programming approach for vehicle maneuvering in tight environments. This is joint work with Francesco Borelli at the Hyundai Center of Excellence at UC Berkeley. So the motivation for this project is it can be quite difficult to maneuver vehicles in tight environments. So it's not, even if you're a trained driver, it's not always intuitive how you should steer to get to where you want to go, because it's very non-linear. So you cannot just go from where you are to where you want to be. And I'll talk a little bit about path planning, our assumptions first, then our optimization approach, and then show you simulation and experimental results, and then talk a little bit about the conclusions from this project. So our assumptions are that, first of all, we want to have a path planner at low speeds, so we can neglect the dynamics, and really it's just a geometric problem of planning the path. So how do you basically need to steer to get to where you want to be? However, we want to consider a general geometry. So that means like we can have a basic a setup of like different obstacles, static obstacles. We're not considering moving obstacles. So one example could be parallel parking, but it could be any kind of maneuver at low speeds. So commercial systems are already available for this situation. However, what if you have like any kind of different geometry from what you planned, and then this becomes a difficult problem? How do you get into the parking space? So dynamic obstacles we consider indirectly by the path velocity decomposition, so meaning like what you would do as a normal driver as well. So if there's a pedestrian walking around, you just stop the vehicle, but stay on your path, stop the vehicle, wait until the pedestrian is gone, and then continue. Or if something moves and then rests somewhere, you just replan your path. So really you don't need to make any obstacle avoidance maneuvers to avoid pedestrians, for instance. However, what we want for the path to satisfy is to be compatible with the vehicle dynamics that you're having. So that means, for instance, if you have this kind of problem, you don't want any like kinks or something that you would get if you use A-star or something. And then we also want to find a good solution, maybe optimal in the sense, to the target position, where optimal can mean many things or a combination of things, like short distance, few changes of directions, a little steering effort, faster drive, and so on. Of course, we wanted to run it in real time on embedded hardware, so it shouldn't take hours to compute. And the path should be easy to follow by a steering controller. So that means it should be easy to find the error from your path. Okay, so just make this projection easy, and then also kind of make it easy to follow in terms of like how the path goes. So for instance, you would want the controller to steer very differently, like if the path is like this or like that. So you want a path that's easy to track, basically. Okay, and then what we do is optimization. Okay, so we're trying to use an optimization approach, and we're splitting the maneuvering problem into a path planning and a path tracking problem. And path planning, we mean we just want to do a single computation or infrequent recomputation. We have a little bit of time, so maybe a second or maybe even a little bit more. We want to use optimization, and we want to use a nonlinear and non-holonomic vehicle model, whereas for the path tracking, we want it to be fast, and we're just using classic feedback control and a linearized model. So this is our approach. So for the path planning part, we're using a kinematic bicycle model, because we're at low speeds, we can assume no tire slip. And if you do that and you actually neglect the dynamic part of the model, you see there's only 3 states for the vehicle, really. And that's what will enable us to use dynamic programming. So what we're doing in the optimization approach is we are actually turning the problem from a ODE into a geometric problem. So we realize that if we keep the steering angle constant for some time, then the vehicle will drive in a circle or a straight line if the steering angle is 0. And we're going to exploit that fact and define a path as a concatenation of arcs. So it's a combination of circles and straight lines. And then really all we need to do is geometric computations, and we don't need to do any ODE solving for finding a path. And that makes it much faster. What is the basic setup? So the basic setup is we have like any kind of geometry with some obstacles in the way. We have a starting position and we have a final position where we want to get to. Now we have defined a path, a feasible path to go there as a combination of arcs. So for instance, in this case, it would be driving to the front, then driving to the rear, and get there. This is just an example. Okay, if we formulate this as an optimization problem, really what we put in as data is the initial position, and then we have some decision variables that relate to the path, meaning like the radius of each of the arcs. Okay, so I is the index for the arcs, the direction we want to drive the arc, and the length we're going to drive, and when we're going to switch to the next arc. And then we have transition conditions in the optimization problem, meaning equality constraints. So the starting position at the next arc is the finishing position at the previous arc, and we have a final condition for where we want the vehicle to be at the end. And of course, what we do have is obstacle constraints. So even though they're linear, it's really an OR connection of these constraints. So to avoid the obstacle, really you only want to satisfy one of the linear constraints. So this makes it a quite difficult problem. So it's actually a nonlinear optimization problem, and it's mixed integer because we need to combine from different sets, and here we need to combine different constraints. Nonlinear, of course, non-convex, mixed integer. So it's a difficult problem. However, you can actually solve it with optimization solvers that are available, and it actually works. However, depending on the problem, it can take very long time, okay, because you have many, many integer variables. So that's why we were looking at using a different optimization approach, using dynamic programming. And the idea is here, really, we split the state space, or we break the state space down into a grid. And as I said before, really the grid lives in 3 dimensions. So it's just x, y, and the orientation of the vehicle, and that makes it approachable by dynamic programming. So I'd say if it's anything higher than 3 dimensions, it gets very hard. But since we can bring it down to 3 dimensions, we can use dynamic programming. And then the idea is to perform a backward search from the final position. So this is where we start our search from, and we're finding feasible arcs to any of the other grid points. And then basically at each grid point store the currently optimal solution to get to the final position. Okay, so in this case we would store this path in this grid point, and we would update the backwards reachable points by checking basically the grid, going through the grid, storing the solution. Only if an obstacle is in the way, so if the computed path hits an obstacle, we say, okay, this is not feasible, and we don't store. And the next step would be like to go from these points, basically backwards, and find connections to other points. And you store the currently best solution in each grid point, so basically straightforward dynamic programming. So you iterate backwards through the grid until you actually reach your initial position, okay? And once you've reached your initial position, you can construct the path by going forward through the grid, because you've stored always the successor node. And actually, if you apply this compared to the other optimization approach, you will get the global optimal solution on the grid. So a few words about path tracking. We didn't spend too much time on it, and yeah, maybe we should have spent a little bit more time. The path tracking becomes quite easy because you can track one arc at a time. You can just linearize the model around polar coordinates because everything is an arc. And you just have a lateral and radial error. And then you define your steering as the corrective steering compared to the arc. And the linearization then leads just to a double integrator that you can control with classic methods like PID controller that you can design actually very well. The vehicle speed along the arc is basically something, or along the path is something that we impose later when we know the path. So it's not part of the path computation. So here's the simulation result. So it's a pretty tight environment. This is the starting position, this is the end position. You have like very little space here, and it's not intuitive how you would get into there. And we want to find the shortest way to get there. And now we run the algorithm, and this is actually the shortest path. So its computation takes about, I think, 300 milliseconds. So it's really fast. So in this case, it's really fast to compute. And it's the minimum distance path to get to the goal. Okay, so it works quite well in simulation. In reality, it was a little bit harder to make it work. And here are some experimental results. So basically, it runs on a car, and this is a test car that we have at the Hyundai Center in Berkeley. So you see, here's the car we're controlling, the gear shift, the steering, and the speed of the car. And we have like some inflatable cars, so it's not so, it doesn't do a lot of damage if we bump into them. And it's just a reverse parking maneuver. And it's just for basically demonstrating that the algorithm works in real time. We try to do more complicated maneuvers as well. And essentially, it would work, but we had some, I'll show you on the next slide, there are some difficulties with controlling actually the controls. So this is something we need to do a little bit more work on. And here you see the problem. The problem is basically like the step responses to what we want to do are very different depending on the speed and the direction and everything where we want to go. So we need to work on this to make it more accurate and predictable. And the same with the steering. At some points during the maneuver, steering is very accurate, and at some points it's not. And so we need to design better steering controller to do it. Okay, so what are the conclusions from this project? First of all, DP can be used for optimization, and it gives the globally optimal solution subject to the grid. However, it would be hard to extend in some senses because DP is restricted to, like, let's say 3 or maybe 4 dimensions. The grid doesn't need to be uniform, so really to utilize it, it makes sense to refine the grid in areas that require high accuracy. The computation time was generally tractable in cases where the environment was very tight and cluttered. So in a sense, it's like complementary to the optimization approach that we also tried with IPOpt, because the optimization approach will have difficulties if it's a tight and cluttered environment, and DP will perform well in these situations because the grid will be relatively small. So DP will not work well in open areas where you need like many grid points and it's not very tight environment. And actually, yeah, if you want to play with it, we have a C code generator online for both the path planner and the path tracker, and a simulation environment, so you can create your own simulation setup with obstacles and run the code and even put the code on a car or something. So yeah, you can download everything. Yeah, that's kind of the end. Thanks very much, and I'm happy to take questions online or offline.
Thank you for your presentation. When you plan the motion in the parking, normally people use kinematic motion, but the kinematic motion is based on fixed velocity. As you show in the presentation, that when you make a command, the vehicle speed doesn't immediately reach to the speed. So there's a discrepancy between your position profile, yeah, and your real motion. So it would be natural when you park the car, you change the slowly the steering instead of using circular motion. So is it possible to use a DP in that application?
Yeah, I totally agree. So we did this to make it actually faster, so that's why we put the commands like this. If we put the commands as ramps, it was slower. But we had behind it we had the idea that we had, I didn't talk much about the longitudinal control, but we had the idea that it would not instantaneously jump like from 0 to 1 or from 1 to 0. Yeah. And yeah, of course it can be, you can integrate more advanced velocity controllers into the algorithm, of course. Yeah.
Thank you.
We have time for one additional question. There is one.
Hello, I would like to ask you, how do you treat the weak trajectories that can result from the dynamic optimization? Because this is an optimization and the result is not predictable, so there can be some trajectories that are not at all natural for the driver. Let's say that the vehicle is turned around and coming back and forth, and then turn around again and coming back and forth, and then getting in the parking place.
Okay. Yeah, it's an interesting question. So maybe it's an advantage and a disadvantage. So in some sense, the algorithm is neutral. So it might think of trajectories that the driver would not think about. Okay. So that could be an advantage and a disadvantage in some cases. If you want to exclude that, if you want to exclude trajectories that are not intuitive to the driver, yeah, I guess it depends. You would have to define exactly what you're allowed to do and what you're not allowed to do in a mathematical sense and integrate that into the problem. Yeah, so I guess it would depend what you want to exclude. So yeah, I cannot give you a more precise answer.
Okay, thank you. We need to move on.
Okay, and so the next talk after, well, the last one in this session will be presented by Ulrich Schwepsiger from the ETH in Zurich, and he will be presenting the topic automated valet parking and charging for e-mobility results of the VCharge project.
Hello? Okay. So thank you for the introduction. I'm Ulrich Schwepsiger. I'm with the Autonomous Systems Lab at ETH Zurich. And I want to talk about the results from the VCharge project, which targets automated valet parking. So the project started in 2011 with a vision that we want to better integrate individual and public transport by offering automated valet parking services, for example, at train stations, airports, or campuses. And the idea here is that the user can simply drop off his car at dedicated VCharge park and ride parking lots, and then the car and the car park takes over, brings the car to the charging station, and the user can directly go on to public transport. Now, to make this really attractive for the end user, we wanted to do this with low-cost sensors only, so no radars, no LiDARs. And you can see the sensor setup that we used here on the right. We had 4 monocular fisheye cameras, which gave us 360-degree coverage all around the car. We had 2 stereo cameras facing front and backwards. And besides that, we were only using the stock ultrasonic sensors that come with more or less every series car nowadays, and wheel odometry. And with that sensor setup, we could actually demonstrate more or less the full functionality that you need for automated valet parking in the end. So here in 2012, it looked still a little bit rough. This was like the first test that we could do. When we finally could glue all the modules together into our very first autonomous run. But then in 2014, we could really demonstrate the whole scenario of automated valet parking in a partially indoors, partially outdoors parking garage at Stuttgart Airport, followed by other demonstrations done in 2015. One time here on the VW campus, an outdoor parking lot, medium scale I would say, and then in the Excellence parking garage at Schiphol Airport in Amsterdam. Now, we've just learned that a system can look much simpler than this with just one building block. When we started the project, also machine learning was not that popular yet, so there are a lot of building blocks in our system. There is a small offline part that we have to do before we can start driving. So we have to calibrate all the cameras with respect to each other and with respect to odometry. We are recording a map containing visual features so we can localize the car in the car park later. We also attach semantic annotations, like a road network and where the parking spots are, to this map. And then a big part of the project was formed by online perception with cameras only. So we were working on occupancy grid fusion, object detection and classification from camera images, and dense motion stereo, so we can get depth information out of the monocular fisheye camera images. Personally, I was working on the local motion planning layer, and our partner at Volkswagen was looking at the automated parking functionality that we need to precisely position the car onto the inductive charging plates. We also had a remote server backend where users could make drop-off and pick-up requests via smartphone. So now I don't have time to go into everything into detail here. Yesterday in the workshop I was focusing a little bit more on the remaining challenges that I see. And today I want to talk about, well, more or less what worked out. So one thing that worked out really nicely was the visual localization in the car park. So we localized the car with cameras only, because obviously in parking garages GPS is mostly not available. And for that we built a map of a sparse map of 3D visual landmarks with associated risk descriptors. And here in the video you can see the 4 cameras of the car hooking up to that visual features in the environment and precisely localizing the car. To add robustness against structural and appearance changes in the environment, we developed an approach that we called multi-session mapping, where we can push new landmarks that we recorded from different times of days and even different times of years in a geometrically consistent way into the same map. And we could show that this multi-session approach greatly increases the availability of localization, meaning the time in which we find enough feature matches that we can still trust the localization. So here you see the localization availability over the range of a full year. And you can see on the upper plot in light blue a single session localization approach, where we try to localize against one map built in the very beginning. And you can see in the beginning we can localize with that map, but like after a month the appearance changes got too big and we cannot use that map for localization anymore. The same happens in the green curve. Here we frequently rebuild a map with a new data set, but we can observe the same phenomenon, that we can localize for a couple of weeks, maybe a month, and then the appearance changes got too big. We could reach the best localization availability with a multi-session approach, where we kept all the landmarks from all the data sets that we recorded. And with that approach, we could reach localization availabilities about 80% throughout the course of a whole year. Now, of course, when you push more and more data into the map, of course the map size grows. So we also investigated into map compression schemes, for example, appearance clustering, where we only keep a fixed number of landmarks from landmarks with similar appearance, or local ranking approaches, where we rate the quality of landmarks based on the number of data sets a landmark was observed in. With the multi-session mapping approach, we achieved, in my opinion, very good localization, metric localization qualities. So we observed maximum translational errors around 10 centimeters compared to differential GPS, and rotational offsets smaller than 2 degrees. So here in that plot, you can see the localization error over a distance traveled of 160 meters. On the one hand, with a single dataset approach, you can see here, where's my mouse? No, I think you can clearly see that with a single a single session mapping approach, we lose localization in some areas, accumulate drift based onto that. But with our multi-session mapping approach, we can reach overall a very good localization accuracy. Here you can see the online perception pipeline for static environments. So we have different sensor sources here, for example, our stereo cameras and the ultrasonic sensors, and output from dense motion stereo from the monocular fisheye cameras. And now we build separate occupancy grid representations out of these sensor sources and fuse them in order to get a complete 2D representation of our static environment. Of course, all of these sensors have different strengths and weaknesses. And we wanted to actually see whether we combine the strength of the different sensors so that we can safely travel around the car park. And here you can see an evaluation whether our fused sensor output can actually detect different objects that we usually encounter in a parking lot. So this is color-coded here. Red is for the front stereo, yellow is for the rear stereo, green ultrasonic, and blue is dense motion stereo. And the stereo cameras are especially well suited for medium-sized objects with texture on it. So we had no problems here actually recognizing those objects located at the left of the slide. Yet we faced problems with a stereo sensor when it came to, more, for example, detecting that wire fence at the upper side of the slide. And also our stereo sensor couldn't detect this arm of the gate that you see on the right side. So I'm not 100% sure why the stereo camera didn't see that arm of the gate. I think in general it should, but we got the stereo sensor as a black box and couldn't really investigate. Maybe that was just a ground plane assumption and that was kind of removed as noise. But for example, the stereo camera cannot really very well measure the width of a parking spot or the occupancy state, just because the way it is mounted to the front of the car and the way we usually approach parking spots, they're usually shielded by other cars parked around. So here the dense motion stereo was really helpful, so we could drive by a parking spot, measure with a monocular camera to the side of the car, and we could do this with around 10 centimeter precision, determine the width of the parking spot. Yeah, so in the end we could cope with most of the obstacles encountered on our parking lot. Just that gate of the arm was kind of a problem. So for the local motion planning part I was working on, I mainly focused on navigation in tight spaces. On parking lots, space can be quite tight. So on the one hand, we focused on highly system-compliant planning, basically to minimize the divergence between what we plan for our eco-vehicle and what it actually executes. Therefore, we used a sampling-based approach where we generated candidate motions via a forward simulation of an identified vehicle model. And we created these candidate maneuvers to be shaped around the reference path with different lateral offsets in order to simulate different evasive maneuvers. On the other hand, we focused on accurate, fast, time-aware collision detection, so we don't lose space for navigation by approximating our vehicle shape with a bounding circle, for example. This is not really feasible for tight parking spots. So we suggested an approach based on bounding volume hierarchies in a workspace that is extended by the time dimension. And with this bounding volume hierarchy, which basically forms a tree of axis-aligned bounding boxes, we can prune a lot of unnecessary collision checks with oriented boxes and use cheap axis-aligned box tests for that and only go into more expensive oriented box collision tests for where it actually is necessary. And With that, we could tackle like platooning scenarios where we were following another vehicle while reacting to static obstacles observed, or appropriately react to crossing pedestrians, where in this example the car just slows a little bit down to let the pedestrian pass. To evaluate the motion planning framework, we automatically parsed around 7 hours of automated driving to determine whether there are situations where our planner actually cannot find a suitable solution. Basically, he thinks all his candidate motions are in collision within the braking distance of the car. Now 7 hours may not seem like a lot, but if you consider that a single mission, so from drop-off of the vehicle to the parking procedure is like 5 minutes usually, these are quite some runs that we analyzed. And for most of the time, the motion planner was just fine, but there were rare occasions where the planner couldn't find a suitable solution. So it was thinking, oh, I'm gonna crash very, very soon. So we manually looked into these situations, and it was mainly situations like that on the right here in the video that are basically completely harmless when you look at the video, but because of noise in velocity measurements of dynamic objects, this reactive approach that we chose doesn't perform very well. So as a result of that, we also switched to probabilistic cooperative motion planning approaches in the meantime that are better able to handle situations like that. Another issue we had to tackle was accurate positioning onto the inductive charging plate. So for an efficient charging operation, we actually have quite strict accuracy requirements for the parking procedure, which are around a maximum longitudinal error of 15 centimeters and 10 centimeters laterally. And for parking, we used like a combination of Reeds and Shepp's curves planning, and for more complex scenarios, a hybrid A-star search. And with that approach, we could stay well within the required accuracy limits. So we got like lateral errors of around 4 centimeters, I think, and longitudinal was a bit higher because the longitudinal dynamics of the car are a bit more difficult to control, around, let's see, 8 centimeters. And that was all measured with this very sophisticated setup that you see here, where we just mounted a pencil at the front of the car and for every maneuver wrote down where the final position of the car was. Yeah, actually very simple and very effective. Yeah, so with that, I'm at the end of my presentation. If you want to go into more detail in any of those topics, you can find me at the poster stand by face recognition, I would suggest. Yeah, thank you for your attention.
Do we have some questions?
Hi. I have a question about the visual localization, and I guess there's some details I'm missing here. Basically, the approach is that you build a feature-based map beforehand, and then use that map to localize the robot, the vehicle. But because I guess the map also includes the parked car. Basically, as this is a changing environment, I understand basically you update the map in the long term. But let's say if some other cars that were previously parked in the parking lot, but actually has already left, if this is not reflected in the feature map, and then if you use this kind of old map to localize the vehicle, potentially it can cause some problems. So how do you
Yeah,
resolve this?
so that is absolutely true. But there I have to say two things. So on the one hand, the localization was very robust against structural changes, I would say. So as long as a big part of the environment has not changed, we don't get any problems there, because we all the stuff that changed we just kick out via in the feature matching step. On the other hand, I think there the multi-session approach kind of comes into play, or the map compression strategies, where we see is a landmark really good for localization, depending on the number of times we see it, for example. And if something changes, we automatically don't see it anymore, and at some time it will get kicked out of the map. So I hope this answers a little bit your question.
Yeah, thank you.
Okay, one quick from the front row.
Could you say something about simplifying constraints used in this project?
Simplifying constraints?
Yes.
Which kind of constraints?
For example, I don't know, processing power or traveling speed or...
Okay, got it. So we were traveling very, very slow. The maximum was 10 kilometers per hour. I think there is some legal regulation which allows driving up to 10 kilometers per hour. Usually we were driving with around 6 kilometers per hour, so we could use the remote kill switch and still walk conveniently behind the car without having to run. We had a lot of processing power in the car. So I think we had like 8 computers in the trunk, from which we maybe really used 4 of them fully. Yeah, other constraints you're interested in? Frame rate for?
Camera.
Oh.
Stereo.
So I can look this up, so we can meet at the poster stand. I don't know it by heart right now.
Okay, thank you. We need to conclude here this session. Remember that all the speakers also have a poster in the poster session. And let's just thank all the speakers again.